So today, and we've had some requests from a couple of you on what is BGP, why do we use it in Calico, what are the advantages, why not something else? So I thought I'd spend a little bit of time today talking about how we make networking simple within the private cloud and how we integrate it with the underlying infrastructure. And that's by using BGP and what our thinking was around that. So that's what we're going to talk about today. If you have questions, please go ahead and raise them. I will try and watch for questions on the Q&A section. But like I said, we'll be talking, so I may not notice them right away. I apologize in advance for that. So I think initially, let's talk about what a routing protocol is in general. This is probably going to be a review for a lot of you, so I'll make it pretty quick. A routing protocol is simply a way to exchange routing information between routers. It doesn't actually forward traffic, right? So BGP doesn't forward traffic, OSPF doesn't forward traffic. Those are two of the most common routing protocols. They simply tell routers, inform routers about how to forward traffic to a given destination. And they do that slightly differently, and that's sort of at least an interesting starting point on the difference between BGP and OSPF. So things like OSPF, ISIS, RIP, EIGRP, if you're a Cisco shop, are all things called IGPs, Interior Gateway Protocols. And things really today, BGP is something called EGP. It's an Exterior Gateway Protocol, and I'll explain the differences, immediately after I get done talking about this. And basically, it's a way of a router or something acting like a router to inform other routers that, hey, I can get to these locations. So a router can tell another router, hey, I know how to get to these destinations. So send traffic to me, or I'm a valid path to send traffic to get to those destinations. That's what a routing protocol does. So that's what a routing protocol does. And I thought it might be interesting to show this not directly initially as a routing network, but let's take a look at international post, and let's talk about how things at international post work, and that actually maybe gives us an interesting way of looking at the difference between an IGP like OSPF and an EGP like BGP. So what I've drawn up here in advance is a theoretical construct of a international postal network. So on this side, we've got China, and I've got a local site in China, Xi'an, and then I've got two international gateways, Beijing and Shanghai. In the US, I've got a couple more nodes. I've got international gateways in Seattle, San Francisco, LA, JFK, and Atlanta. In reality, there are more, and same as in China. This is just to make things simple. In the UK, I've got London as an international gateway. In the US, I have local sites, Denver, Omaha, Chicago, and in the UK, I've got Sheffield. So let's talk about how this works and routing within this mechanism. Now, in the postal environment, this is all what's called statically configured. You know that Seattle can get to China through Peking and Shanghai. That's something that they know because they set up the routes, but let's assume that this is more of a routing network. So Peking and Shanghai, Beijing and Shanghai, have connections to Seattle, San Francisco, and LA. And let's just make this interesting. Shanghai doesn't have connections to Seattle, and let's say Peking or Beijing has all three. So Beijing and Shanghai tell Seattle, San Francisco, and LA, I know how to get to everything in China, so send everything addressed to something in China to me. Similarly, in the UK, there are connections between London and JFK and Atlanta and LA, and London tells those three cities, those three US gateways, I know how to get to everything in the UK. You don't need to worry about where it is in the UK. It's in the UK, just send it to me. Great. So now let's say we have someone in Omaha that is trying to send traffic to Xi'an, China. It's trying to send a letter to Xi'an, China. So this is the source, and this is the destination. So the local carrier picks up the mail, takes it to the sorting center in Omaha. That would be considered like a local route, like my subnet. A host on my subnet is trying to get traffic out. It has a default route to its local router, its top of rack switch or whatever, and that would be, in this case, Omaha, the Omaha routing center. Omaha says, okay, well, this is going to China. Now, Omaha has learned, and I'll draw that out specifically, Omaha has learned that to get things to China, it needs to send them to Seattle SFO or LAX. And the way it learns that is in routing is something called IBGP, which we'll talk about in a minute. But it's an important distinction. So Omaha has learned via interior BGP that to send things to China, it needs to send to Seattle, San Francisco, or LAX. So then Omaha goes, well, how do I get traffic how do I get that letter to Seattle, San Francisco, or LAX? And what it's going to do, it's going to learn that its ability to reach those locations, it can send traffic to Chicago, who has access to San Francisco and Seattle, or it can send that letter to Denver, which has access to San Francisco or LA. A key point here is, as far as Omaha is concerned, Seattle, San Francisco, and LA are exactly the same. They all have ability to get to China. So at this point, Omaha just needs to figure out the most efficient way to get that letter to one of those three cities. And let's say there's a flight leaving for Chicago in 30 minutes, and it has a direct connection onto Seattle. The flight to Denver is going to take longer. It doesn't leave till tomorrow morning. This is an express letter. So Omaha puts the letter on the plane to Chicago. Gets to Chicago, and Chicago goes, this is going to China, and takes a look and says, well, it'll get to, if we send it through Seattle, it will get there faster than San Francisco. So the letter is put on the plane to Seattle, and Seattle says, well, I know how to get this to China. I send that to Beijing. So it goes on the plane to Beijing, and in Beijing, the letter will get delivered however it gets delivered within China, and eventually ends up in Xi'an. So that is a postal route where you've got more specific information within the country. Sites within the country know how to get to everywhere within the country, but they have very limited view of other countries. And they rely on these gateways to deliver the traffic to those countries. And in turn, those gateways rely on their matching gateways in the other country to do the final delivery. So that is a very simplified version of a postal network, and it's a little bit of white lies, but it's a good point. This is also the way networks work. So, don't have any questions so far? It's good. I need a little bit of coffee. And I apologize for the noise outside. The construction is still going on outside our studio's conference room. So now let's turn this into, first of all, let's look at the different types of routes in this infrastructure. One are the routes between these countries, and we'll call those external routes. So these routes and these routes are external. The routes that told Omaha, to send the traffic to Seattle, San Francisco, or LA, i.e. China, is behind one of those. Those routes we'll call internal. And the routes how to get to those nodes we'll call local. It's not quite the right terms, but it allows us to talk a little bit about them. So an external route, the only difference is since Omaha doesn't know how to get to Shanghai at all, we can't tell Omaha all Chinese mail goes to Shanghai or Beijing, because Omaha theoretically doesn't know how to get there. So that's the job of the gateways within the country itself to say, hey, I can get to China. I know how to get to China. So on these routes, the gateway sets something called next hop. It says, I know how to get to China. Send all traffic to China to me. Send all letters going to China to me. I'll get it there. For LA, San Francisco, or Seattle telling Omaha where to go to deliver traffic to China, that's the route that they'll tell. So PVG will tell LA, send traffic to me. LA will tell Omaha to send traffic to LA as well. So we'll call all these internal, actually. There's going to be a distinction I'll make later. Now, Denver, Chicago, Omaha will, what I now need to know is Omaha needs to know how to get to these places. So instead, now Omaha has to know specifics. It knows it needs to get to Seattle, San Francisco, or LA, but now it needs to figure out at this point in time what's the best way to get there. And that's an internal route. So Denver says it can get to San Francisco and LA, and it's going to cost this much time, effort, etc. Chicago says it can get to Seattle or San Francisco with this much time or effort. And they're both going to tell Omaha that. And then Omaha can take that information and make a decision which of these three gateways is the best one to send the letter to. That is called an internal route, and that is a full topology. Omaha now understands that where it's going to send the traffic, what's involved. It knows the specifics of how to get there, whereas the external route is just saying, get it there. It doesn't say how, it just says get it there. So in this case, the internal routes are more specific and change more frequently as flights take off and leave or get delayed or weather or whatever else, whereas the gateways never change. The gateways are always saying, send China to me, send China to me, or send UK to me, send UK to me. So that's the difference. Denver is not necessarily going to tell Omaha to send traffic to China to Denver. It may, but it may not. And we'll talk about how that might happen in a second. So I'm just using these routes to get to one of the gateways. Let's take a case now where you're in a small town in Nebraska, and we'll call that, there's a town in Nebraska called Valentine. Valentine is really a spur at the end of the network. And let's say its only postal connection is through Omaha. It's not true, but let's say it is. In that case, what we might do is have Omaha say that it knows how to get to both China and the UK. So now, instead of Valentine seeing Seattle, San Francisco, LA, JFK, Atlanta as the gateways, Valentine's going to see Omaha as the gateway for everything. And then Omaha, in turn, will figure out which gateway to send it to. So this is acting a little bit like a route coming across the gateways. So we now have spurs or endpoints, and we have something like an intermediate routing node, like Omaha, and then we've got gateways. So hopefully that makes sense at this point. So now let's talk a little bit about how this, let's flip this story now and say this isn't a postal network. Let's say this is a routing network. So what are the equivalents here? So the equivalents are what takes the place of a country in an IP network is something called an autonomous system. There are numbers, they're handed out by the same folks who hand out your IP addresses, the registries. You can also have private ones, so you can have private address space, RFC 1918 address space, you can have private ASs. So let's say this is AS1, and this is AS2, and this is AS3. The same things apply. All of these routers are in AS1. All of these routers are in AS2, and all of these routers are in AS3. So in this case, the way BGP, so these are the three ASs. To get traffic between ASs, these external routes use BGP. Therefore, BGP was originally designed to send traffic between routers, between ASs, excuse me. These blue routes I drew up in here are internal routes. They're routes that tell you how to get to a gateway. So these internal routes, you would use an IGP. And the most common examples for that would be OSPF or ISIS. RIP and others fall into this as well. So OSPF and ISIS will tell you how to get to a gateway or how to get to something within my AS in most cases. We'll get to a little example in a minute. Actually, I'll get to it now. BGP was designed to handle very large aggregates of traffic flowing between two ASs. Lots of addresses, lots of routers, because you have this is public internet, right? So you now have thousands and thousands of routers or millions of routers in the global internet. BGP is designed to handle that. It's a bit slower detecting failure, and it's really focused on where you're going, not how to get there. So BGP is very efficient to do that job. The IGP in a normal network, or a standard wide area network, let's not say normal, it was originally conceived for, does a lot more. It detects faults very quickly. It also keeps track of all the different paths that you might use to get somewhere, calculates which one's the most efficient at that point in time, and is constantly sending lots of updates. And it was meant to deal with a small constrained network, i.e. a single autonomous system. That might be a service provider, it might be an enterprise, etc. But so it's a constrained environment, whereas the world, the public internet, a network of ASs is an unconstrained environment. I don't know how big it's going to get because other people control most of it. I only control part of it. That's another way of thinking of ASs, by the way. An AS is the things within your control. So an IGP passes a lot of messages, changes state very frequently. Therefore, it doesn't scale all that well. It's designed to handle a limited number of destinations and a limited number of routers. So if I now had the global routes in my IGP, I'd have a problem with scaling. Normally an IGP might be talking about thousands of routes at most, and tens to maybe 100 type the scale of routers. Whereas BGP talking public internet, you're talking hundreds of thousands, 500,000, million, couple million worth of routes, and an unknown, unbounded number of routers potentially in the system. So very different scales. If you think about it, as we're going from VMs, which are small, and servers, small number, fairly static, that may fit this model a little better. When we start talking about cloud native and hundreds of thousands of containers that are coming and going all the time, that starts sounding a little more like the BGP problem space rather than the IGP problem space. First hint as to why we picked BGP here at Tigera for Project Calico. So the IGP is doing all that. But now we have a problem in that Omaha needs to tell Valentine that it can get to China and it can get to the UK. But we said we're not putting these global routes in the IGP because we're going to blow the IGP up. Plenty of examples of being able to blow up OSPF out there in the world. Go read the NANOG lists. It's fairly frequent when people make that mistake. They haven't made that mistake in a while. So what we've done in the routing protocol space is we made a distinction. eBGP is the BGP you run between ASs. There's another flavor of BGP. It's called iBGP. And this is running within the AS, and it's just used to tell someone like Valentine that Omaha can get to everything, or can get to some set of everything. So again, we're telling Valentine, send all traffic to me, and I'll get you there. So that's one use of iBGP. Another use of iBGP might be for LA and San Francisco and Seattle. We'll get to that in a minute. But there's another use of iBGP where you might use it to spread more specific reachability information. And we'll get to that when I actually draw a real network diagram. So does this make sense so far? Is that we sort of explained between an IGP and a EGP, or specifically BGP, why you would use it, the concepts behind it, specifically the scaling. So when we looked at the problem space that we were addressing with Calico, we decided that BGP was the right approach. It's simpler. People think about BGP as being a complex beast, and it can be, but in its simple guise, it's actually simpler than an IGP. IGP has a lot more moving parts. BGP is a very simple thing. Send all this traffic to me. That's all it's really saying. The rest of BGP's complexity is something called policy, and that's when BGP gets complex. So the simple thing of Beijing and Shanghai telling Seattle, San Francisco, and LA, hey, send traffic to me, that's a couple of lines of configuration in BGP. What we also allow you to do in BGP, and it's not available in an IGP, is to put business logic in BGP, and that's called policy. So it might be that Beijing and Shanghai tell these routers, Seattle, San Francisco, and LA, to send traffic for China. Let's say I have another AS over here, and that is some other country. Not going to pick on anyone in particular. And it's got a router that's connected to Seattle. And normally that router says, I know how to get to everything in AS4. Let's say either through malfeasance or just misconfiguration, all of a sudden, so normally the route being told here is, I know how to get to AS4. Send AS4 traffic to me, and that's the route that's being propagated to AS2, to Seattle. Let's say they make a misconfiguration, and now it also says, send traffic to me for AS1. So normally this router would go, okay, well, there's another path to China through AS4. Odd, but okay. And if it's the cheapest path, guess where the traffic's going to go? That way. That allows somebody to siphon off traffic from AS1. It allows people to, you know, like I said, siphon traffic off, or just black holes traffic that was supposed to go here, because let's say there's no connectivity there. So you can put policy in these routers, and you can say, I will only listen for AS1 routes from Beijing and PBG. I'm not going to listen to it from anywhere else. So when AS4 tells you to send it traffic for AS1, you'll ignore that message. That's a very simple version of policy. Another version of policy might be that Beijing tells Seattle that across that link it only wants to receive express mail. So if traffic from Seattle going to Beijing is an express letter, it will take that path. If it's not express mail, then Seattle will send it to San Francisco, which can send regular mail to Beijing or to Shanghai. So there's many different ways you can do this. Let's say another very common use case in networks is transit. So another thing that policy can allow you to do is you can say, does the US Postal Service want to be in the business of allowing traffic from the UK to use the US to get to China or not? If it doesn't, the routers in JFK and Atlanta who know how to get to China through Seattle SFO and LAX won't tell London that there is a path using JFK and Atlanta to get to China. And maybe then London goes through Hong Kong or directly to Shanghai via some other matter, and that's how mail gets there. But let's say the US Mail Service wants to be in the business of selling connectivity between the UK and China. Then JFK and Atlanta can tell London to send traffic to us to get it to China. We're a valid route to China. And that again would be controlled by policy. By policy, you could say, I'm only going to send my routes to London, or I'm going to send other people I'm connected to's routes to London as well. And that's all done by policy. So this is when BGP gets complex, is when you start writing these business logic rules into the routing protocol. We're not going to do too much of that in a cloud infrastructure because it's a simpler network. I'm not in the business of selling transit, etc. usually. So a lot of that complexity that we've built into BGP to handle those cases, we just don't turn on. And you really do end up with just a couple of line config to make BGP work in a private cloud environment. So with that, I'll pause a couple seconds for questions. Okay, got one here about why not use, what's the problem with using OSPF to do all of this? And I'll go into a little more detail with that. OSPF is sending a lot of messages all the time, and the messages are very specific. It's not send everything to China to Denver. It will be very specific and say, send all of these locations to me in Denver. There's a lot of locations back here in China. And I can only encode so many of those locations in a given message. Message sizes are scoped, are limited size in OSPF. Any network packet, really. So now all of a sudden, I'm sending lots and lots and lots of messages just to say, you know, Xi'an is here and Nanjing is here and you know, Huan is here, and all of those locations would now be sent as specific messages between Denver and Omaha. And same thing for, you know, all these locations in the UK, enumerated and sent. And every couple of seconds, checking to make sure you can still reach those. So that really, really spins those protocols hard, and they just will not scale. BGP is a much more laissez-faire approach. It says, everything over here, just send it to me. And we'll check it every 30 seconds to see if it's alive versus seconds or sub-seconds. So it's an order of magnitude at least less just health checking as well. So OSPF, the rule of thumb in a given area in OSPF, 50 to 100 routers, thousands to maybe 10,000 routes. And in a cloud scale environment, that's too small. And so you're just going to be spending a lot of compute to do things you really don't need to do, because we already understand the topology in a private cloud environment. So anyway, that is BGP, why people think it's complex. We've introduced eBGP and iBGP, and I'll explain what those actually are in a second, what happens. And we've talked about IGPs. We introduced the concept of ASs and local topology versus global topology. So I think at that point, we've explained the basics of BGP. So now let's talk a little bit about how this actually works. This is a wonderful, pretty picture here. Let's talk about how this might work in a classical CLOS, L3 CLOS, or L3 leaf and spine topology in a data center. Any more questions before I erase this? It's gone, it's gone. Okay. At least till Mike puts a recording up and you can go back and look at it again. So let's draw your putative data center. So we're going to draw 3 racks. And each of these is the top of rack switch. And I'm going to draw the Kubernetes use case here with Calico, just so everyone understands. And then off of this top of rack switch, I have some number of hosts. Some number of hosts here. Some are usually in the order of 30 to 60, seen as low as 20, I've seen as high as 110 hosts in a rack. The open compute guys can really jam a lot of hosts into a rack. As can some of the Blade folks can cram an insane number of nodes into a rack. So I've got some number of hosts, got top of rack switches. I'll build a couple of spine switches here. And there are other topologies that can be used to top of rack switch. M-lagged spines. There's a number of different topologies, and we actually have some classes on network design and some consulting. So if you're interested in exploring this in more depth, definitely reach out to us. You might even get to see me in person doing more detail on this. Again, I'll leave it to you to decide if that's a good or a bad thing. And up here somewhere, I probably have a border router or data center gateway that's talking to the rest of the world. That's rest of the world up there. So these are spines. And I've seen there's lots of designs out there where there's actually 2 tiers of this. There's all different types of topologies. So we'll make this connection. We'll make this connection. More than happy to talk about CLOS leaf spine, but I'm going to assume most people understand that at this point, so I won't do it here. Reach out to us if you have questions about how this part of this all works. Now, standard network. So let's say for my infrastructure, I'm going to use 172.16.0.0/16. So that's where my infrastructure is set up. So we'll say that this is, I'm just going to do the last two. This is 0.2, 0.1, 0.3, 0.4. Then this one is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. The way you address these, and are these L2 or L3, very variable. I'm just going to use that these are L3 points up here. They don't have to be. This is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. Makes sense? So let's say down here, I'm going to say this is 16.1/24, 17.1/24, 18.1/24. Basically means this guy is going to be .2, .18, let's say, 16.2, 16.18. This will be 17.2, 17.3, 17.4, 18.2, 18.3, 18.4. I'm using all V4. This all works the same V6, so I'm just using 18. May feel a little more comfortable with V4 addresses than V6 addresses. We'll be talking later on this year about V6 in cloud native. So if you're interested in V6, I think that's sort of at the end of this month or early next month. Look at the schedule on Tigera.io resources webinars. You'll see the schedule. I don't know if the V6 one is up yet or not. If it's not, it'll be the one after the last one in the list. So at this point, there's going to be some routing going on. How this is set up in your infrastructure is sort of however set up your infrastructure, but we're going to make the assumption everything is running BGP. Let's talk about the Bgp topology a little bit. The model we normally suggest is every rack is its own AS. And I said ASs are assigned globally via the registries. There's also private AS numbers, and there's about 500 of them in the what's called 2-byte AS space. Think of it as the IPv4 of AS numbers. And the IPv6 of AS numbers called the 4-byte AS. There's 49 million private ASs that you can use. And the good thing is that this only affects routers. No one else needs to know about it. And all routers today support 4-byte ASs. So depending on your size and scope, you could use 2-byte ASs or 4-byte ASs. I'll use the 2-byte ASs here. So let's say this rack is AS 65.500. Actually, no. We'll do 65.510. This rack is AS 65.511. And AS 65.512. And this switch might be AS 65.502, 65.503, and 65.501. Now these could all be in the same AS. It could be in different ASs. Just using the logical extension, which is an AS per every routing entity within this network. And we'll talk about why that might be useful in a minute. So at this point, this top of rack switch 1.2 and 2.2 is going to send a BGP announcement to the spines, which are separate ASs, US to China, saying, I know how to get to 172.16.16.0/24. So at this point, these two switches know that, and let's look at the routing table here. Let me go over here. So the routing table in these top switches is 172.16.16.024 has a next hop of, depending on which switch it is, either 172, which spine has it, .1.2 or 172.16.2.2. And its AS path is AS 65510. So at this point, these two switches know they use either 1.2 or 2.2, depending on which one we're talking about, to get to AS 65510. And knows that AS 65510 encloses 172.16.16.0/24. So I need to make these bigger. I know Mike's going to yell at me later, so I'll try and make these bigger as I go on. So at this point, and the same repeats for all of these. These switches will probably tell this switch, using BGP, that they know how to get to AS 65510 and its networks. So another transit switch might have, so we'll call this routing table A. We'll put that up here. And we'll just use this case. So routing table B, which is here, will say that 172.16.16.0/24, the next hops it's going to now know from 2 are 1.3 and 2.3. So it now has two paths to get to it. It can get to that network via either of these, and it is going to have an AS path of AS 65502 or 3, and AS 65510. So I now know I need to get to 2 ASs to get there. And again, the actual route, I'll just be specific here. For 1.3, the AS path is 65502, 65510. For the route to 2 via 2.3, the path will be 65503, 65510. So that's the routing table in B. And we replicate this all the way across. Now, normally, the way these hosts get set up, so right now, say the host in C, we'll pick 2 hosts in D. So the routing table in C will usually just have a default learned for the DHCP or whatever else that says 0, 0, next hop is 16.1, and D's routing table will say 0, 0, everything goes to 17.1. And then as it learns about other hosts, it will know specifically that 16/24 is local. So it won't use that default routing table. One of the things in IP, I made the assumption, just to point out real quick, IP will always prefer the longest prefix match. So if I have two routes here, default will only be used if none of the other routes will match. So whatever route is most specific is the one that IP picks. It's a very useful tool. So we now have routing. What we do in Calico now, it gets a little interesting. I'm not going to explain all the Calico details, but Calico turns every node into a router. For VMs, or in the case we're talking about in Kubernetes, pods, but Calico nodes aren't switches, they're routers. So in that case, I've got a router here that speaks in private cloud BGP. Also in some of the public cloud instances, it speaks BGP. I'm not going to draw this everywhere, but I'll draw it here. So I have a router here. That router is going to peer with its top of rack switch. It already speaks BGP. There are other ways to do this, but this is the way I'm going to be talking about. So this router peers to that top of rack switch. This top of rack switch performs two functions. It acts as a router to the rest of the network, and it acts as a route reflector. For things in its local subnet. Let me explain what route reflector does really quickly. Remember I said BGP routers will only say I know how to get to these things. They're not usually used to tell you how to get to them. Therefore, a BGP router, the assumption in BGP is if I'm in the same AS, if I'm the outside router, the router that sits across an AS boundary, I will change the route that I tell you, which you just saw here, to say I'm the next hop. So in this case, this router is telling B that it is the next hop for what this switch told it, because there's an AS boundary in between. If there's no AS boundary in between, which there wouldn't be here, it's not going to say that it is the next hop for a given destination. And that's on purpose. We don't want routing loops within an AS. The assumption in BGP is that all the BGP speakers within a given AS will peer with one another. And that's fine. But if you have a lot of switches, a lot of routers down here, that's configuration. And we automate that in Calico. You don't necessarily automate it up here, depends on the switch. So there's another approach which we developed in the IAP community quite some time ago called a route reflector. And a route reflector simply says that within an AS, you peer with the route reflector. The route reflector will not change the next hop route. It won't say send traffic through me. It will simply just tell you the next hop for that is this other router in your same AS. So to make configuration simple, we treat these peerings as route reflector peerings. So now in Calico, let's say I've got pods here, and those pods are in 1064.0.128/26. And down here I've got pods that are in 1064.8.0/26, and pods over here are in 1064.4.128/26. So what's going to happen is this router, 16.2, will tell this top of rack switch that it knows how to get to 1064.0.128/26. So in this case, this router here, this switch here, will get the route of 10. So I need to do this one. I'll call this one Z. I'm out of space. I'm going to get rid of this other AS here just to make more space. So routing table Z now has all the routes we talked about before, but it also has now a route that says 1064.0. So we'll say this one. This is more interesting. Let's say this is the one that's announcing right now. So it has a route for 1064.8.0/26. The next hop is 16.3 or 18, I said, because there's more switches there. And the AS path is local. You're within the same AS. So that's what the route, this top of rack switch was acting as a router and a route reflector. This is what Z has. Z will then tell C exactly the same thing because it's a route reflector. It's not going to change its next hop. So C will now learn that 1064.8.0/26 is locally reachable on 16.18. At the same time, this router will tell the other ASs, in this case A, that 1064.8.0/26 is next hop to itself. So I'll get that as 1.2, and the AS path is 65510. So now this switch will tell B that it is the next hop. So we'll say 1064.8.0/26. Its next hop 1.3, and its AS path is 65502, 65510. So now this switch knows that to get to pods in this address, it needs to send it to one of these two switches. These two switches know to send it here. This switch knows to send it here, all by following BGP announcements. Similarly, C knows how to get there as a local route. It won't send it through the switch. Now, it'll go to the switch for L2, but it sees that as a local, so ARC for 16.18 and send the traffic directly to 16.18, which knows how to send it to that pod, to a pod properly addressed. So now everything understands where all the pods are. Here's a key advantage of using BGP versus an overlay. Everything knows how to get to that pod. No encapsulation or de-encapsulation necessary. Let's say off of this spine, I have a NetApp filer or a database or something that is bare metal, isn't in my cluster, and it's trying to reach a pod down here. These switches know how to get to 1064.8.0/.5, this pod. So literally, he's going to send traffic, he's going to follow his default. Somebody's unhappy in that construction site. I don't know if you guys can hear it. He's going to send traffic to that switch. That switch knows to send that traffic to this switch, which knows to send it here. No on-ramps, off-ramps. This all just works because the pod's addresses are in the same address space as the rest of the infrastructure. We're coming up really close to time, but this is basically how BGP works within Project Calico. We have some documents on how to make this that go into this in a little more detail. There are a couple things to keep in mind. Routers within an AS don't change their next hop to other BGP speakers. So it's assumed that you know how to get to those destinations. When you cross an AS boundary, you do change the next hop. You say, I'm the next path, rather than saying, talk to him, because this device may not know how to get to there. So that's one thing. eBGP does something called set next hop self. When it announces out, it says the route that it's learned to other BGP speakers, there it is local AS, it will say, I'm the path to that. Whereas if it's within the AS, talking to another router within the AS, it will not say I'm the next hop to that unless it's learned it from an external route. So these two routers, this router will not say I'm the next hop between 2 and 18. That's one thing. Two, in order to prevent loops, BGP will not install a route that has already gone through its AS. So if for some reason you ended up sending traffic from 65510 to 65511 and ended up coming back to 65510 as a routing announcement, I will not install a route here if it came from another AS. A perfect example of this, some people want to reuse ASs, and you can do that. So every rack is 65510. And I have 65502, 65503. The problem is any router in here will not install, this router would not install a route for 1064.4.128/26 because the route, what this guy would see is 1064.4.128/26. It's going to see the next hop it will have learned from here as 16.1. That's good. It's going to see an AS path of AS 65502, AS 65510. The problem is he also thinks he's 65510. So when he sees his own AS in the AS path, he'll think, oh, this is a routing loop. I should know the direct path to this, so I'm not going to install this route. Now you can tell routers to install the route anyway. That's a bad idea because you now can introduce the chance of getting routing loops. So if you're going to reuse the same AS for each rack, you need to be careful such that the routes don't appear to come from this AS, but the routes appear to come from the spines. And that gets around this problem. There are two ways of doing that. Only announcing default, because default's usually originated up here. So these guys don't get the more specifics, they just get default. That's fine, they send traffic to the spine, it goes back down. Or by doing something called strip AS path, it's a configuration to most routers. And if you want to get more details of that, let me know. And at this point, I think that's all the time we have. I have to go jump on a plane and route myself up to Portland. So before I get off this topic, I'd like to thank you all for watching today. Hopefully it was useful. If you have any questions, please reach out to us, myself or Mike. And with questions, we'll be happy to answer them. Like I said, we've got some network design classes as well, training as well at Tigera if you really want to dive into the nuts and bolts of this. And we have some documents on docs.projectcalico.org around some of this basic architecture, around this BGP architecture as well. So with that, thank you very much, everyone. I don't see any other questions. So I'll return you to the rest of your day. And thank you for watching. Have a good day.